In this video, we're going to talk about inverse and composition functions. And we're also going to look at some special examples of important functions at the end that'll have some important relevance, especially in applications for computer science. Okay, so first, let's talk about inverse functions. So if f is a bijection, remember bijection means it's one-to-one and onto, then the inverse, which we use this f to the -1 notation, is the function that literally reverses the domain and codomain. And f inverse of y equals x if and only if f of x equals y. So it's the idea that it takes the ordered pair under f and reverses it the opposite direction. It maps it the other way from the other set as the domain to the previous one's codomain. All right. So it's kind of a cool thought. It's not complicated though. And if you've worked with inverses before, you probably have recognized this. Let's real quick, I do want to say that there is this phrase invertible. So a one-to-one correspondence is called invertible because we can find an inverse of this function. In other words, it's really important to say that if you say a function is invertible, you're implying that it's one-to-one and onto, because we're saying it has one-to-one correspondence, or the other phrase is bijection. That's what they used in that definition there. Okay, so let's look at some examples. Let f be the function from ABC to 1, 2, 3 such that f of a equals 2, f of b equals 3, f of c equals 1. Is it invertible? And if so, what's the inverse? Okay, so because this is kind of listed, I'm going to do one more time where I set up like a little picture for this one. Okay, so here's A, B, and C. And then over here is 1, 2, 3. I don't know why I floated these letters so weirdly. So weird. Okay, we'll pretend that wasn't as weird and awkward as it seemed. Okay, under the function, A goes to 2. Here, sorry, let me use my red. A goes to 2. Boop. B goes to 3. And C goes to 1. Ooh, okay. So it is one-to-one, right? Since two things in the domain aren't going to the same thing in the codomain. Also, all of the elements in the codomain are being used, so it's onto. So the answer is it is invertible. And that's because it's one-to-one and onto. It works. Okay, cool. Now that we know it's invertible, they want to know what the inverse is. Okay, so remember just what we saw a second ago. The inverse is taking and reversing the order of each element in the codomain and mapping it back into the domain. Okay, so here, real quick, if this is A and this is B and F, oops, I want to do it in red because I'm trying to be consistent. F matches or maps A to B. Then the inverse goes the reverse direction, B to A, and it literally maps each one of these in reverse. So F inverse of 1 is going to be C. F inverse of 2 is going to be A. And F inverse of 3 is going to be B. So notice I focused on the elements in the codomain B, and I listed those and reversed their patterns. I looked at the pre-images, to use another terminology word that we talked about in the last video. Cool, but literally, I'm just swapping these. Just swapping the ordered pairs here. Really, that's all I'm doing. All right. Okay, so let's look at some more complex examples. Let F map Z to Z. So we're only looking at integers only, okay? So f of x equals x plus 1. Let's determine if whether or not it is invertible. And if so, what is the inverse? Okay. So is it 1-to-1, right? If I take something and plug it in for f, any z, right? So I pick something, an integer in, let's do -1, all right? I'm going to get out, let's see, 0. All right. And the question is there any other integer I could plug in and get out 0? And the answer is nope, that's it, just -1, right? There's nothing else I'm going to be able to plug in to get 0. So since that's the only one that works, this is 1-to-1. So 1-to-1. Now, is it onto? That's the question. Is all of the elements in the codomain, the Z, do they have something that maps to it? So here's the idea. If I pick something, an integer, could I figure out what equals it? So if I pick some random integer, let's call it 4. Can I figure out what x has to be? Well, the answer is yes, because I can solve this equation. I set x plus 1 equal to 4, and I'm like, ooh, x equals 3. So if I plug 3 in, it goes to 4. So I can do that with every integer. So this is onto. So it is 1-to-1, and it is onto. So that means it's invertible. F is invertible. Okay, so let's figure out the inverse. So what we're trying to say is, if we take something in our integers under F, right? What happens to that something? So if something's over here, if x is over here, it gets mapped to x plus 1. So whatever x is, it's always going to be plus 1. So if I want to go the reverse direction, I want to start with something here. How do I get it back to this? Well, the answer would be I'd need to -1 to get it back to that. So F inverse of y equals y minus 1, where I'm talking about y being in the codomain and x being something in the domain, all right? But that's how you would write the inverse for it. All right, let's try another one. Let f equal or map from the real numbers to the real numbers, then, or f of x equals x squared. Is it invertible? And if so, what is the inverse? So let's start with 1-to-1. Is it 1-to-1? So the idea is if I plug in, like, let's say 1. No, here, let's pick a more interesting number. It's too boring. Let's do 2. I plug in 2, I get out 4. The question is there anything else I can plug in and get out 4? And the answer is, yeah, -2. That's a problem. 2 numbers are going to that same element. So it's not 1-to-1. Therefore, F is not invertible. All I had to do is show one example, and it's non-invertible. So I can't find the inverse. Now, if I were to limit my domain, that would be different. In other words, if it wasn't all of R, we would be okay. If they were to limit the domain to R plus all the positives, it would work. But that's not what they asked. I'm not going to change it. So it's not invertible. Okay, let's look at compositions of functions. So composition is the idea that we are taking 2 separate functions with 2 different mappings, but the thing that connects them is that they have G, in this particular case, maps A to B, and F is going from B to C. So it's this idea that we can kind of go from A to C. That's what's happening under the composition. We can map from A into C. And the way that it's done is, first thing we do is we start with A, and G takes us into B. Then from B, F takes us into C. So we can go from here all the way to here. That's how composition of functions works in this kind of higher level set thinking. Okay, you probably remember this. Let's do some old school examples to kind of get it back into our heads how this works. So let's suppose we want to look at this composition. F of x is x squared, g of x is 2x plus 1, okay? And because we are just looking at functions, we're going to go ahead and assume that it's going from real numbers to real numbers for right now, all right? F is mapping from the real numbers into the real numbers, and G is mapping from the real numbers into the real numbers. Notice we don't have to worry about one-to-one or onto for this. Okay, so let's do this. If I want to find F composed of G, based on what I wrote up here in the definition, F composed of G is F of G of X. So F of, well, here, let me write F composed of G, sorry, by the definition, equals F of G of X. So that means I'm taking G of X, which is 2x plus 1, and I'm plugging it in to F of X. So I'm taking 2x plus 1, and I'm plugging that in to X. So that means I'm going to take that and square it. So this equals 2x plus 1 squared, which if I FOIL that out is 2x plus 1 times 2x plus 1, which is 4x squared plus 4x plus 1. Cool. There we go. Now they want us to go the reverse direction, G composed of F. So that means we're taking F of X and plugging it into G, which means I'm taking X squared and plugging it into G. So this time the X I'm interested in is I'm plugging to this X, and that ends up being 2 times X plus 1. So in this case, instead of 2 times X, I'm doing 2 times X squared plus 1. And there's actually no way to simplify that. So that's done here. There's my 2 answers. There's F composed of G. There's G composed of F. Okay, let's look at some more exciting examples. This one is where we kind of are doing the map from ABC into 1, 2, 3. Okay, and they gave us the map is F of A equals 3, F of B equals 2, F of C equals 1. Okay. Now they want us, oh, I just realized they didn't give us G. No, I didn't give you G. So here, let me give you G. Kind of need G, all right? G maps ABC onto itself. So onto ABC. And G is, or I should say G of A is B, G of B is C, and G of C is A. Sorry, I didn't realize I had missed that. I might fix this before I post the video so that you have that up. Sorry about that. You may not even have to write that. Okay, here we go. So let's do this. We want to find the composition. F composed of G and then G composed of F. So let's start with F composed of G. So what we have to do is we have to do each mapping as it makes sense. So remember, F takes ABC and maps it to 1, 2, 3. G takes ABC and maps it to ABC. Okay, so F composed of G means I'm going to start with G and end up using F. So G gets used first. That's what that means. So I'm going to start by finding F composed of G of A, which means I'm looking for F composed of G of A. Well, G of A happens to be B. So this becomes F of B. And F of B happens to be, highlighter, 2. Let me highlight. There we go. 2. So this equals 2. And there we go. We got F composed of G of A. So now I have to do that for B and C. I have to do it for all 3 of these elements, A, B, C. Okay, so we're going to find F of G of B. Okay, so G of B. Sorry, let me erase these highlighters this time. Come on. I know you can do it. There we go. All right, G of B is C. So this is going to be F of C. And F of C is 1. So this equals 1. Yay, we did it. We're amazing. Okay, do it again. This time for C. Okay, F of G of C equals, okay, so G of C, last one is A, and A, F of A is 3. So this thing equals 3. Okay, so there we did it. We did the composition of F composed G. This all makes up F composed G. Okay, now let's look at G composed of F, the other direction. G composed of F. So that means we start with F first. That's actually a problem because F maps A, B, C into 1, 2, 3. But G starts with A, B, C and ends in A, B, C. So if I try to do like G composed of F of A, I'm sorry, I meant A. G composed of F of A, all right. I would get G of F of, okay, so F of A is 3. I still have that highlighted. And, oh, sorry. Which is 3. But G doesn't map 3. G only maps A, B, and C. So this is a problem. It's not possible. So we can't do this. Not possible. All right. So the way the domains and codomains are set up does matter. All right. It does matter. All right, let's look at another one here. This one we have F of X equaling 2X plus 3, G of X equaling 3X plus 2. They are defining to be on integers only. We're going to talk about that soon, by the way, when we're not defining it over every real number. All right, integers only. So here's what happens. Nothing. It's going to look just like we did before. F composed of G. So we actually did one really similar to this at the beginning. So this is going to be F of G of X, which is F of 3X plus 2, which I'm going to plug in 3X plus 2. I'm going to plug that in right there for X. So I'm substituting that in for X. So that's going to be 2 times 3X plus 2 plus 3. So I'm taking this and I'm plugging it in for X. See how that's matching what we have highlighted there? It becomes the new X. All right, so here, get rid of all those and let's simplify. So this is going to be, let's see, 6X, and then that's going to be 4 when I distribute the 2, right? So 6X plus 4, and then that 3 will combine with the 4 to give me 7. All right, I hope you're okay with me skipping the step. There we go. G composed of F is plugging F of X into G, which means I am plugging in 2X plus 3. So it's the reverse direction this time. So this time I'm taking 2X plus 3 and I'm substituting it in for X here on G. So I'm plugging it right into here, this. So that's going to end up being 3 times 2X plus 3 plus 2. So simplifying will give me again 6X, but this time plus 9 when I distribute the 3, right? And then 9 and the 2, those 2 will add up to 11. So we do get 2 different answers. That's fine. That means, by the way, that composition is not commutative, right? They don't equal each other. All right. But there we go. So exciting. Okay, now we're going to look at some important functions that we'll use as examples a lot. But before we do that, I wanted to comment, or they actually kind of take some time to comment on what it means to define things over Z and not R. So when you're defining a function like 2n plus 1, where n is coming from Z, that means we're looking literally at single points. In fact, we can even look at the plane, the XY plane, or R squared, as these individual single points, and we're filling in only the ones that actually pertain to 2n plus 1. So we're not connecting the dots, we're just looking at those ordered pairs only. When we look at something like x squared, again, just the ordered pairs under that mapping. All right, that's what it means to look like what it is in Z. So if it was R to R, we'd be connecting those dots, right? We'd be drawing our parabola, but we're not. It's Z to Z. Okay, now that we've got that, here's our function that we're going to focus on. We have a couple functions, but this one's kind of the big focus. It's the idea of what's called a floor function and a ceiling function. So please note in here, let me zoom in a smidge so make sure we can see that. Do you see how this bracket is extending under here, under the X? That's indicating that it's almost like got a floor, right? But over here, the little bracket is extending on top. So that's the ceiling. All right. Here's how it is defined. The floor function is the largest integer less than or equal to X. The ceiling function is the smallest integer greater than or equal to X. Here, let me zoom out a smidge and let's look at some examples. So one is looking at the less than, one is looking at the greater than, but really what it's looking at is the integer that it's closest to. So this first one, A, is looking at the floor function for 3.5. So the integer that's closest to it, but smaller than the number, is 3. For 3.5, the ceiling, the integer that's closest to this number, but bigger, is 4. Okay, so here, the integer that's closest to 1.5, negative 1.5, but smaller than it would be negative 2, right? It kind of goes the opposites for negatives. But the integer that is closest to negative 1.5, but bigger than negative 1.5 is negative 1. So you have to kind of do the opposite for the negatives. Visually, it ends up looking like these little step functions. They kind of end up being these steps where everything from 2 to 3 is just this whole number 2 when we're looking at the floor function. So this is the floor function. And this one's the ceiling. So from 2 to 3, everything is getting rounded to 2. Over here, maybe I should have picked a different number since it's, oh, no, it is. Okay, sorry. Over here from 2 to 3, everything is getting rounded to 3 because it's the ceiling function. So when you're between the numbers 2 and 3, if you're looking at the floor function, you're going to round down. If you're looking at the ceiling function, you're rounding up. Did they mention? Oh, yeah, sorry. I skipped over this note and I didn't mean to. The floor function is often called the greatest integer function in a lot of books, including most calculus books, and it's denoted with both of the little tails on top and bottom, but it's really referring to the floor function. I have also seen it denoted with a double bracket like this. I have seen that as well, and that's also called the greatest integer function, which this book is referring to as the floor function. Okay. There is some table in the book that kind of lists some of these useful properties. I'll let you go through that. There is a proof that is useful for this. Well, not useful, but good practice for us on how to prove something. And it uses a concept that is going to kind of help prepare us for what we'll be seeing in the future. Here's the idea. If we want to prove that in this floor function, 2x is going to end up being the same thing as taking the floor function of x plus the floor function of x plus 1/2. All right, let's look at an example really quick of this. Like, let's let x equal 3. Okay, and this is not my proof, but I'm just going to kind of write this down just to kind of give myself a second. So if x equals 3, that means we're saying that the floor function for 6 equals the floor function for 3 plus the floor function, the floor function for 3.5, right? If you're doing 3 plus 1/2 or 3.5. So here, I'll write it as 3.5. Okay, so 6, the floor function for 6 is just itself. The floor function for 3 is just itself. But 3.5, the floor function is 3 because it's going to round down. So that's going to work. Yay, it works. Okay, so that's not exciting. It's exciting when X happens to be something like a decimal. All right, so here, let's look at a decimal example. Let's do 3.5 now. Or here, let's do 3.2. Ooh, so exciting. 3.2. Okay, so this time then, what we're doing is we're doing 2 times 3.2. So 2 times 3.2 is 6.4. And then we're saying that's going to equal 3.2 plus, okay, so that's 3.2 plus half, which is 0.5, or 3.7. I hope we're comfortable with that. I've been thinking of this as 0.5 rather than half. Okay, so that's a 3.7. So 6.4 under the floor function is going to be 6 because it's going to round down. And this one's going to be 3 because it's going to round down. And this one's going to be 3 also because it's going to round down. So it works. Okay. So the idea is that what we're worried about is maybe if the decimals get too high, it might not end up working. Okay. What if that 1/2 ends up pushing it over? Okay. So we're going to set up a proof for this. And here's how that will work. We're going to say that, sorry, my mind shut off there for a second. I apologize. We're going to say X is some number plus a little bit extra, okay? N is an integer, some nice whole number, but epsilon, this epsilon here, is a decimal of some sort, okay? So we're going to say then that epsilon is bigger than or equal to 0, but less than 1. So it's a decimal value. So there's 2 cases. Case 1. Let's look at when epsilon is less than 1/2 or less than 0.5. Let's say 0.5. Yeah, let's say 1/2. It's fine because they have the 1/2 in there. Okay, so if if epsilon is less than 1/2, so we're at the 1/2 mark and below. It's technically below 1/2, which means that when we plug it into here, right, if it's below 1/2, it's not going to bump us up to the next integer. All right, but we'll deal with that in a second. Okay, so here we go. So based on this statement right here, 2x, oops, sorry, 2x equals 2n plus 2 epsilon, right? I just multiplied everything by 2. Now that I did that, I want to look at what the integer function is for 2x. So I'm looking at what the integer function is going to do to 2n plus 2 epsilon. So if I take and multiply epsilon by 2, is that going to be a whole number or bigger than 1? And the answer is no. Epsilon is smaller than 1/2. So if I multiply it by 2, it's never going to get up to 1. So 2 epsilon is smaller than 1. So this is going to end up equaling 2n because it's going to round down. This is like a number plus a little bit like 0.8 or 0.9 or something, right? But it's not going to be enough to bump it up to the next integer. So this thing is going to end up being just 2n, whatever this is, this whole number, because it's an integer, right? It's a nice whole number, and this is some decimal. And so it's going to round down to the integer like it did earlier when we were looking at those problems or examples. It will not let me erase this underline for some reason. There, yay, let me do it. Cool. All right. So now that I looked at the 2n, the floor function for 2x, okay, I need to look at what happens when I'm focusing on x plus 1/2. X plus 1/2. So here, I'm going to come back up to this thing, which I just now circled. And if I add 1/2 to it, that means I could just add 1/2 to the other side. Do you agree? Plus 1/2. Cool. Okay, so if I want to look at the floor function for this, All right, the floor function for this, x plus 1/2. Well, then I'm looking at what's happening with n plus epsilon plus 1/2. Okay, so this is a nice whole number. The question is this going to exceed 1? As long as it stays less than 1, it's going to round down to n, right? And the answer is it's not going to exceed 1. Epsilon plus 1/2 is going to be less than 1 because epsilon is less than 1/2. So for the same reason we just talked about above, it's not going to end up being bigger than 1. So this whole thing is going to equal n. Okay, so here's what we got. So this 2xn ends up equaling 2n. Oh, sorry, I forgot the other piece. I'm so sorry. I forgot this piece right here. So I showed this piece and I showed this piece. Now let's look at that piece. So if x equals n plus epsilon, then the floor function for x is going to equal what happens to n plus epsilon, but epsilon is less than 1/2, so this is just going to end up being n. Okay, there we go. Sorry. So now we're ready to say that the floor function for 2x ends up being 2n, and the floor function for when you take x and add it to the floor function for x plus 1/2, that ends up also equaling 2n because both of those equal n. Oops. So they work. They're equal. That's when epsilon is less than 1/2. The problem is we also have to look at when epsilon is bigger than 1/2. Let me see if I gave myself enough space. Yay, I did. Okay, so this is case 2. Case 2. When epsilon is bigger than or equal to 1/2, we'll go ahead and allow it to equal 1/2 on this one. Okay, now this is where they get a little tricky, all right? You would never have known to have done this. I'm just going to tell you that right up front. And that happens sometimes with proofs, which is why they show them to us so that we can learn these little tricks. Okay, so the same way I did before, I'm going to still use x equals n plus epsilon, where epsilon is between 0 and 1, but less than 1. Okay, great. Still using that. So I want to look again at 2x. Okay, so again, 2x equals 2n plus 2 epsilon. And I'm like, well, that's nice. The problem is, since epsilon's bigger than 1/2, we have a potential issue with this going over into the next one, right? Since epsilon is bigger than 1/2, this thing, oops, oh, sorry. Sorry. Since epsilon is bigger than 1/2, this thing is going to be bigger than or equal to 1. Which means this is going to bump up the floor function. So this is going to end up being too big to say that it's 2n. It's going to end up being 2n plus 1, the next integer up. This is going to bump it up into the next bracket. Now, the way the book does this, I'm going to show you their trick. They take this statement here and they say, if I think of this as 2x equals 2n plus 1 plus 2 epsilon minus 1. So what they did is what's called a put and take. They added a 1 and then subtracted the 1 in the same statement. And the reason they did that is they were like, okay, cool. That means that I can think of this as 2n plus 1 and 2 epsilon minus 1. So when I look at the floor function, this thing here in the second part, this is going to be less than 1. So this is going to end up being 2n plus 1 when it pops out, because this part, 2 epsilon minus 1, since epsilon is bigger than 1/2, that's going to come out to something that's bigger than 1, but this result is going to end up being less than 1 overall. So that's how the book does it. I think the way I just argued it is a little bit cleaner, so we're going to go with that. I'm going to do it again here in just a second. If it kind of felt a little confusing, let's try it again. Erase all that stuff. All right, here we go. So let's look at x plus 1/2. Actually, here, let's look at x. Okay, so x, which is n plus epsilon, is still on the floor function going to be just n, because epsilon, even though it's bigger than 1/2, it's still less than 1. So this isn't going to exceed into the next integer. Okay, great. Now let's look at x plus 1/2. Coming back to this thing again, add in the 1/2. Okay, so this is going to be x, n plus epsilon plus 1/2. Now this thing right there is going to pop up and be bigger than 1 again. It's bigger than or equal to 1 because epsilon is either 1/2 or bigger than 1/2. So the lowest it could possibly be is a 1. So it's going to be bigger than that, which means that when I look at the floor function for x plus 1/2, then I have n plus epsilon plus 1/2, and that's going to end up being n plus 1. It's going to end up pushing it into the next integer bracket. So it's going to be 1 bigger. All right, so here we go. We're almost there. So 2x, the floor function for 2x is 2n plus 1. And the floor function for x plus 1/2 is n plus 1, or 2n plus 1. So they're equal. We did it. All right. Okay, so last special example. This is called the factorial function. If you haven't seen the factorial, oops, looks like a little exclamation mark. All right, and here's what it means. You're taking every number from 1 up to n, and you're multiplying them. They made a note, by the way, that 0 factorial is 1. So here, for 3, then under this function is going to be 1 times 2 times 3, which is 6. Or 6 factorial is 1 times 2 times 3 times 4 times 5 times 6, which is 6 times, sorry, I'm going to group them up here. So this is 6, that's 20, and that's 6. So 6 times 6 is 36. 36 doubled is 72. Add a 0, 720. You can grab your calculator and double check that. In fact, you may want to grab your calculator to figure out the next one. And it's possible your calculator has a factorial key. If you're using any of the TI calculators, like TI 84, 83, something like that, okay, you would go under math, and it's one of those options under math, like it's the 5th or 6th option under math. And it's looks like a little exclamation mark. So if you put 20 exclamation, go to math and then go to exclamation mark. And math, by the way, is under like the 2nd button or the alpha button. I can't remember. It's on the top left in the row. So just kind of search on the top left row. Okay, 20 factorial ends up being a huge number, which I pre-calculated to be 2432 902 008 176 640,000. Okay, that's the exact number. So let's see, millions, billions, trillions. Wow, I don't even know. Isn't that sad? I'm never used to writing numbers even that big. Your calculator is probably using scientific notation if you tried to put it in, because the number is that big, and it's not going to give you so many exact digits as even this is. But that's what 20 factorial comes out to. It won't really work with anything that big without a computer, but it gives you an example of this function. And we're going to be looking at factorials later on.